7/10 of the Earth's surface is covered by water, moving all the time, always wearing away the land. The countless streams and rivers also wear away the land as they move. They carry tiny pieces downstream into the sea. If we take a sample of seawater, we can see some of this material. Yet, even after the bits have settled, a single taste tells us that there is still salt in the water. This salt was once solid material. We cannot see it. It's finer than the finest sand or clays. We'll take a little of this water and evaporate it under a heat lamp. The camera speeds the action. We see crystals appear. These crystals are minerals that were dissolved in the water, minerals that were dissolved in the sea. The sea, then, is really a tremendous solution. Do you know any solutions? How do you use them? To have a working idea of solutions, let's first learn some definitions. We say that a solution has two partners. The sugar, in this case, is the solute, the substance we will dissolve. The water is the solvent, that is, the substance in which the solute is dissolved. Here are three important ways to know a solution. The first is that the solute is broken down to the size of molecules or ions. Second, the bits of solute and solvent are spread out evenly and stay spread out. Third, a solution can be made stronger or weaker. The concentration of solute and solvent can be changed. Let's look at point 1, the size of the particles. Into the smaller container, hanging in water, we drop some soluble crystals of potassium compound. Almost immediately, the crystals begin to dissolve, becoming ionic in size. The water molecules bounce the crystals around. They're spread out evenly to make a purple water solution. The solute particles in a solution are so small that they come through filters with the tiniest holes. The part of solution we filtered is the same as the original solution. If we divide our solution into 4 exactly equal parts, each part contains exactly 1/4 of the solute we originally dissolved and 1/4 of the solvent used. Let's take the same solution and divide it into 10 equal parts. Each part has exactly 1/10 of both solute and solvent. So, in a solution, solute and solvent particles become and remain evenly spread out. A third characteristic of a solution is that it may be made weaker or stronger by using different amounts of solute or solvent. Here we've added a few crystals of a copper compound to water, making a very dilute, weak solution. If we add a large amount of solute, we say we have a concentrated, a strong solution after it is dissolved. If we keep adding solute until no more will dissolve, we have a saturated solution. Does a solvent dissolve all substances equally? No. Different solutes do not dissolve equally. Carbon does not dissolve in water. We say it is insoluble. Let's try calcium hydroxide. Very little dissolves in water. It is slightly soluble. The chemical sodium sulfate is dissolved 1 part to 10 parts water. Such a material is soluble. Finally, when we use sodium hydroxide, there is more solute than solvent in the solution. We call the substance very soluble. Ability to dissolve depends also on the solvent. Let's try the solute copper sulfate in 3 solvents: oil, petroleum ether, and water. The salt, copper sulfate, as we saw earlier, is soluble in water. Can oil dissolve copper sulfate? No. Copper sulfate is insoluble in oil. Now we will use oil as the solute. Will it dissolve in water? No. Oil is insoluble in water. Let's try oil with a different solvent, ether. Oil is soluble in the ether. There are a few simple rules about solubility. One general rule: an organic substance, like oil, will dissolve in an organic substance like ether. An inorganic substance, like table salt, will dissolve in an inorganic solvent like water. Like dissolves like. Physical factors also control solubility. One factor is the particle size of the solute. Here are 2 large crystals of the same solute. We'll grind 1 crystal to powder. We use equal amounts of the solvent, water. We place a whole crystal into 1 beaker and the powdered crystals into the other. We can see that the finer the material, the more rapidly it dissolves. Shaking or stirring a solution makes the solute dissolve faster. Other physical factors affect the way solutes are dissolved. Generally, heating a solution causes more solute to be dissolved. Here, the heat makes it possible to keep dissolving copper sulfate even after the solution can take no more at room temperature. Does heat always increase solubility? In this soft drink, a gas, carbon dioxide, is dissolved in the liquid, water. Let's heat the soda. As the liquid is warmed by room temperature, bubbles of gas come out of solution. As we heat the solution, more bubbles of gas are driven off. The solubility goes down. So, heating decreases the solubility of a gas in a liquid. Another physical factor is pressure. This drink is bottled under pressure, so that more carbon dioxide gas will dissolve in the liquid. Increased pressure increases solubility. So far, our solutions were of solids in liquids, such as a salt in water. We also saw a gas dissolved in a liquid to make a solution. Are other kinds of solutions possible? Can a gas be dissolved in another gas? We can mix chlorine in the bottle with bromine vapor, for example. As they mix, the particles of each gas become the size of the molecules. They're spread out evenly. We can change the amounts of each gas. So we have a true solution. Another kind of solution is one we saw before. Oil dissolved in petroleum ether is a solution of one liquid in another liquid. Knowledge about solutions can be useful in many ways. We know that solutions of an acid and a base, when mixed, can neutralize each other. The exact point at which neutralization takes place depends on the concentration of each solution. If we know the concentration of one solution, we can find the concentration of the other solution. With this scale and measuring flask, we have made a normal solution of sodium hydroxide, a base. The weight is measured exactly for the amount of water, that is, 1 liter. The 1 liter of this base can neutralize 1 liter of a normal solution of any acid. We'll use this idea to find out how concentrated the hydrochloric acid is. Let's fill the measuring flask with exactly 100 milliliters of the hydrochloric acid. Fill it a little more. Then bring the level down, drop by drop, to be exactly 100 milliliters. The acid is poured into the flask. Now we add a dye. You will see this dye change color as the acid reacts with the base. This measuring tube shows lines which measure milliliters and parts of milliliters. Now we pour in the base, the sodium hydroxide. We fill it a bit more, then take out a few drops. We read 1 1/10 milliliter and jot the figure down in the notebook. And place the acid under the measuring tube. Now we drop the base, whose concentration we know, into the acid, whose concentration we don't know. Notice the careful drop-by-drop work. The color changes from red to yellow. The base has completely neutralized the acid. Let's read the difference to know how much base we added. We had 31 1/10. Subtract 1 1/10. It took 30 milliliters of normal base solution. So the acid must have had the same, 30 parts. Now, by mathematics, we find out the concentration of the acid. In this case, the acid solution was only 3/10 normal. This method of checking strength of a solution is called titration. Titration is done daily in laboratories and in industry where solutions are used. Another use for solutions is in cleansers. A solution of carbon tetrachloride, for example, is a solvent that will dissolve grease and so remove it from the cloth. Everyday solutions include antifreeze in your car, perfumes of many kinds, and many common medicines. Sometimes we may want to separate one or more substances from several in solution. In organic chemistry, the process of distillation is often used to separate the parts of a solution. A second useful method of separating solutions is to cause the solute to settle out of the solution as crystals. By heating the solution in the dish, we can reduce the amount of the solvent. This is evaporation. The camera speeds the action. We see the crystals of the solute appearing. The process of crystallization is used in many ways. The table salt you use may have been crystallized from a salt solution. This metal, magnesium, was produced in this plant from magnesium salts, which were crystallized from seawater. Although solutions have been used for centuries, science has much more to learn about them.